The next topic in energetics is what we call Hess's Law. So Hess's Law looks at that enthalpy change of a reaction depends only on the identities of the reactants and products. Another way to say it is that the pathway for the reaction or the enthalpy change is independent of the reaction pathway. So how you get from point A to point B doesn't matter. And this means that enthalpy is something that we call a state function. So Hess's law is essentially the law of conservation of energy applied to these chemical reactions that we've been looking at. Another way to describe it would be to look at it like this, that if you're going to convert A into B and then B into C, and those are two different chemical reactions, the first change will have a certain enthalpy change to it, and the second will have a different enthalpy change to it. Now, if you can also do the same net reaction, if you can convert A directly into C, that will have a different enthalpy change. But they should all be related. The total change to get from A to C should be set in stone as this delta H3. And so these two smaller enthalpy changes should add together to equal that third enthalpy change. So that's the entire principle, really, of Hess's law, that when you have a change from initial reactants to final products, the total enthalpy change is the same whether or not you get there in one step or in a series of steps. Okay, so this is the mathematical relationship between changes in enthalpy. Now, what that's going to allow us to do is, if we want to know what this third enthalpy change would be, well, if we can measure these first two enthalpy changes, we can add them together and know what this enthalpy change should be without ever actually having to carry it out experimentally. We can also, if we know enthalpy change 1 and enthalpy change 3, then we can solve for enthalpy change 2 without actually carrying that out experimentally. So it's just a useful thing to calculate enthalpy changes that sometimes are difficult to carry out experimentally. Drawn another way, like on an enthalpy level diagram, if the y-axis here is enthalpy, H, then the idea is to get from A all the way to C. That has a certain enthalpy change, again, being noted by delta H3. And if you get there in a series of smaller reactions, then you're going to have the initial change and then the second change, and those two will add up to delta H3, just like it says in this equation up above. So the amount of enthalpy in A and the amount of enthalpy in C, those are set in stone based on what they are. And so the change to get from A to C is a certain amount, whether we do it in one reaction or in two reactions. So this is a way to represent Hess's law visually, but it's not really the way that's going to get used on the IB exam. It's just one that we're sort of familiar with. The way that it's normally going to get represented on the IB exam is with something called an energy cycle. Unfortunately, the IB uses many different, slightly different shaped energy cycles with arrows pointing in different directions, which is kind of a pain. But if we look at the first one, it ends up being sort of like vector math for any of you, or vector like you would use in physics. So the way the first one works is to get from A to C, right, is one enthalpy change, or you can go from A to B and then B to C. And that shows us that this enthalpy change plus this enthalpy change, we get to the same point C. So I guess the way that I try to tell people to remember is that there's always going to be one arrow, right? And then there's going to be two arrows. I guess that's the normal way. Now, notice that the start of our energy cycle here, we have the two sort of butt ends of two arrows. So that's the start. I shouldn't write with my marker, but I'm doing it anyways. So that's the start of the energy cycle. And down here where two arrowheads meet, that's the end, right? And so when I say start and end, I'm kind of referring back to this idea of a point A and a point C, okay? And so the change to get from A to C should be the same whether or not I do it in this one step or whether or not I do it in these two steps. like so. So again, look for where the two butt ends of the arrows are and the two arrow heads are, and you'll know where the A and C are, where the start and the finish are. So this is another energy cycle, represents the exact same thing. I see that here are the two butt ends, okay, and here are the two arrow heads. So these two, 1, 2, should add up to this third one. Okay, so there's one that goes directly from the start to the end, and that's the overall enthalpy change. And then there's these two other ones that take an extra step to get there. And so those two should add up to this third one. If we do it again, I can see the two butt ends, and I can see the two arrow heads. So this one does it in one step. So there's our delta H3. These two do it in 2 steps, so these two together should add up to that one. Okay, and one last way that I've seen it done on the IB exam, 2 butt ends here, 2 arrowheads here. Therefore, here's the direct one. Here's the direct overall change. And here's the 2-step one. And again, you've got these two adding up to these two. I know that it's a little easier in my diagram. It's color-coded, and I kept labeling them 1, 2, and 3. Note that on the IB exam, they probably wouldn't be noted as 1, 2, and 3. So you'd have to figure out which enthalpy changes add up to which other enthalpy change. So again, look for the butt ends of the arrows and the arrow heads, and that can help you a bit. The other method that gets used with Hess's law, I think it's a much simpler method, but your information is not always presented this way. What's really cool is that it works out. If you can take 2 chemical equations and add them together, and just like we've done before with like redox half equations or reaction mechanisms, if something is on both sides of the arrow, then it cancels out. So when we add A turns into B and B turns into C together, we end up with a B on both sides of the equation. So we cancel the B part out of the net equation, and we get A to C. So notice that this was kind of the simplified way we looked at it before. A to B and B to C is the same as A to C all in one step. Well, it actually works out that way if you follow our rules for adding equations together. A to B plus B to C, we cancel out the B's because they're on both sides, and I end up with this being the net overall equation. So if I add 2 chemical equations together, then I add their enthalpy changes together. So when I added these two together, I'm going to add delta H1 and delta H2, and delta H1, delta H2 therefore equal delta H3 for that third reaction, just like we said back at the beginning. If this is delta H3, so literally when I add these 2 chemical reactions together, the 2 chemical equations, they add up to this third equation, and therefore if I add their 2 enthalpy changes together, it adds up to the third enthalpy change. If you want to see an actual chemistry example, if you have nitrogen plus oxygen and you make 2 nitrogen monoxides, that would have a certain enthalpy change. 2 nitrogen monoxides plus oxygen can then make 2 nitrogen dioxides. That has a different enthalpy change. If you add the 2 equations together, you can cancel out the nitrogen oxides. That sort of ends up acting like an intermediate would. We cross it out and we get this as the net equation. And so even if I never do this third reaction, I can know that the enthalpy change for this third reaction is the enthalpy change of the first reaction plus the enthalpy change of the second reaction. So if I add them together, I'll get the enthalpy change for this reaction. So if you can add chemical equations together, you cancel out things that are on both sides. The net equation that you make will have this, the enthalpy change will be equal to the sum of these sort of component enthalpy changes. So the way that I already sort of mentioned what we use Hess's law for, it allows us to calculate enthalpy changes theoretically that are impossible or nearly impossible to carry out experimentally. It also allows us to confirm and compare how our experimental enthalpy changes match up to ones that we can calculate theoretically. So it can give us a sense of how accurate our theoretical models are. But more really on the new syllabus that we have, really it's just going to be about this first one. You're going to use Hess's law to calculate enthalpy changes and usually they're ones that are tricky to calculate experimentally. So in terms of accuracy, you've noticed that there's a lot of questions in energetics that ask you to compare different methods of calculating a delta H. We've seen questions already. They talk about, what's the problem with using bond enthalpies, or what's the problem with using calorimetry to calculate enthalpy changes. Assuming that we're using the most up-to-date, accurate literature values available, like the ones that are in your IB data booklet, then Hess's law is extremely accurate. Compared to bond enthalpies, you're using enthalpy changes that are really specific to the reactions in your questions, whereas bond enthalpies are, first of all, averages, so they're not specific to certain compounds, and they're only semi-accurate for the gas phase, and so any other phases involved, and bond enthalpies get really inaccurate really fast. And comparing it to using your own calorimetry data, we know that your own calorimetry data has a huge amount of systematic error, especially heat loss to the surroundings. So Hess's law is going to give you, is based on much more accurate experimental data, and so it gives you a much more accurate value in the end. So it's really, of all the methods that you learn, because it's based on accurate literature values, it's going to give you the best and most accurate answer for your questions. Okay, so practice examples, just as an initial one. Calculating the enthalpy change for this reaction here is really tricky to carry out experimentally. Carbon reacting with oxygen to produce only carbon monoxide. So we know that if we burn carbon and oxygen, we make carbon dioxide, and we can incompletely combust it and make some carbon monoxide also. But forcing carbon to only produce carbon dioxide when it burns is pretty tricky. So this is a sort of questionable, tricky enthalpy change to measure experimentally, but we can solve for it with other enthalpy change values that are really simple to carry out experimentally. So carbon reacting with oxygen and completely combusting to make carbon dioxide, that has an enthalpy change value of negative 394 kilojoules per mole of carbon that gets burned. It's also relatively easy to take a pure sample of carbon monoxide that you obtain and combust that to make carbon dioxide. And that has an enthalpy change of negative 283 kilojoules per mole. So the question is, how can we solve for the unknown enthalpy change, this one, using these known enthalpy changes? So one way to do it is with an energy cycle. Again, the energy cycle is they probably most commonly use looks like this. And what we're trying to do is think about, okay, what's sort of the beginning of this cycle, the two butt ends of the arrow, and what's sort of the end point where all these reactions end up. So for me, I would look at this cycle and think of it's sort of a cycle for oxidizing carbon. Now, sometimes you'll be asked to come up with your own energy cycles. For an example like this, they'd probably fill in the energy cycle for you, since it's not sort of a standard type of enthalpy change. Anyways, let's try to think through it. Sort of the original point for me is carbon by itself. And what we're looking at is that we can either take carbon and oxidize it all the way to carbon dioxide in one step, which is represented by this reaction, or we can take carbon, oxidize it to carbon monoxide, and then we can take the carbon monoxide and oxidize it to carbon dioxide. So let me write that out in the energy cycle. If we take carbon, we can turn it into carbon monoxide, and then we can turn it into carbon dioxide, or we can do that directly all at once, right? And obviously there's some oxygen involved, so we need an O2 molecule in order to completely combust it. To turn it into carbon monoxide, I need half an O2 molecule. And to turn it from carbon monoxide into carbon dioxide, I need half an O2 molecule. So what we're seeing is that we can either do this change from carbon to carbon dioxide in one step, or we can do it in two half steps. Okay? And so the point is, the enthalpy change here and here should add up to the enthalpy change over here. So if I fill in the enthalpy change values, we know that going from carbon to carbon dioxide is negative 394 kilojoules per mole. That's just copied down from up above. We also know that going from carbon monoxide down to carbon dioxide is negative 283 kilojoules per mole. And so the one that we don't know is this one, but the concept is that these two changes should add up to this third change. So it ends up being some pretty simple math that negative 394 should equal negative 283 plus whatever that last enthalpy change is. And so if you solve for that, you get negative 110 kilojoules per mole equals X, or equals that third enthalpy change. And if you think about it, I said negative 110, not negative 100. If you think about it, that does make, I suppose the numbers have changed slightly. I'm stuck in the past. Negative 111 would be the enthalpy change. So it must be that this releases negative 111 kilojoules per mole, because this change only releases negative 283 kilojoules per mole. And in the end, I know that this change is negative 394. So since net you start at carbon and you end at carbon dioxide, the total enthalpy changes should be the same. If you want to do the simultaneous equation method instead, we know these two equations, and what we need to do with them is try to make them add up to the equation that we don't know the enthalpy change for. So that equation is up here. So I'm going to grab it. I would like to grab it all. No, that's not going to work. So looking at the two that I know and the one that I'm trying to find out, I need to figure out a way that I can manipulate these two equations that I know so that when I add them up, they add up to this equation. Remember, the idea is if you can make equations add up to a third chemical equation or a fourth chemical equation, then you can add up the enthalpy changes to add up to the enthalpy change of the last equation. So the way I do this is I see that in the final equation I have a carbon solid on the left, and I look at my equations up here and I have carbon solid on the left in the first equation. So for me, that looks like I'm going to leave this first equation alone. It looks like it's oriented properly if I want to add these up to the third equation. But then if I look at the second equation, I notice that the carbon monoxide is written on the left, whereas in my final equation it's written on the right. So what I'm going to do to make the math work is I'm going to take this equation and I'm going to flip it. Well, that's what I call flipping it. You're going to reverse it. So you're going to have CO2 on the left, and you're going to have CO on the right, and you're going to have the oxygen on the right also. And when you flip an equation, you flip its enthalpy change. And I'll go over that again, but essentially, if I instead write the equation this way, then instead of the enthalpy change being this, it ends up being positive 283 kilojoules per mole. So I have an equation here where it's negative 394. I have the equation now here. I'm no longer using this equation. I flipped it, and so now I've got this is my enthalpy change. If I add these two equations that I have written now together, notice that the CO2s are going to cancel out because they're on each side of the arrow. 1/2 O2 is going to cancel out. So it's going to leave me with a half O2 on the left. The carbon solid is going to come down on the left. And the CO is going to come down on the right, exactly where I want it. So now, because I flipped that second equation, when I add them, they add up to this equation. So when I add these two enthalpy changes, they should add up to the overall enthalpy change. And when you know it, if you add negative 394 with positive 283, you get negative 111 kilojoules per mole. So whether you want to approach it from an energy cycle standpoint and figuring out the overall change versus the two component changes, or if you do the simultaneous equation way where you end up flipping these equations around and multiplying them, you get to the same final answer. And I think we're going to stop the video there. Never mind. Okay, one thing I meant to show you before the simultaneous equation, so I'll show it to you now. Just a reminder about enthalpy changes. In terms of doing the simultaneous equations, but also just as conceptually, it's important to know how you can rework these chemical equations and how they'll affect the enthalpy changes. So reversing a process or a chemical equation reverses the sign on the enthalpy change, but the value stays the same. If you think about this change being shown, water melting, solid to liquid, or liquid going to solid, the amount of energy change is exactly the same, but if you're going from solid to liquid, that would be a positive endothermic change, and liquid to solid would be an exothermic change. So the enthalpy change when 1 mole of ice melts is always, or when it freezes, is equal in magnitude, but when it melts, it's positive, and when it freezes, it's negative. So flipping this chemical equation or this physical process right here, it's an opposite enthalpy change. The enthalpy change when 1 mole of methane forms is represented by this chemical equation, and the enthalpy change is negative 74 kilojoules per mole. So then if you flip it, the enthalpy change when 1 mole of methane unforms, I guess is how you could say it, or breaks apart, it should be the opposite of that enthalpy change. So that would be represented by positive 74 kilojoules per mole. On an enthalpy level diagram, right, again, the enthalpies are set in stone. So carbon plus 2 hydrogen molecules has a certain amount of stored chemical energy, and a mole of methane has a certain amount of stored chemical energy. So whether or not you are forming or unforming that compound, the enthalpy change is set in stone. It's just a matter of direction that makes it positive or makes it negative. Another important thing about reworking these chemical equations is that multiplying them means you multiply the enthalpy change by the same amount. So if you combust methane, it releases negative 891 kilojoules per mole, or it releases 891 kilojoules for burning the 1 mole. If you double everything, in the energetics topic, you have to really pay attention, because if you double the coefficients, you're now saying that I'm burning twice as much methane. And burning twice as much methane, burning 2 moles of it, releases twice as much heat. Notice it doesn't say kilojoules per mole anymore. The enthalpy change is just written as kilojoules. So it's twice as much. And if you change the coefficients to be halves or fractions, then you have to multiply the enthalpy change by that change in coefficient. So only burning half a mole of methane will release half as much energy, so it will release negative 445.5 kilojoules. So when we do the simultaneous equation approach, you are allowed to flip chemical equations, because when you flip them, like this change from here to here, I refer to this as a flip, right? You make the products reactants and you make the reactants products. You also have to flip the enthalpy change. So negatives become positive and positives become negative. When you multiply chemical equations, you're allowed to multiply their coefficients by whole numbers or by fractions, right? When you do that, the same change applies to the enthalpy change. So doubling the coefficients implies doubling the amount of energy released, and halving the coefficients involves halving the enthalpy change. So that's really important when we do the simultaneous equation approach. That's what I did here when I flipped this equation. I flipped or reversed its enthalpy change, and we'll see that you're allowed to do that in more complicated examples as well.